Hi, and welcome to the next lecture unit in the lecture chapter on Gaussian processes. And this lecture unit is mainly only on the Gaussian process training, which is on how we do hyperparameter optimization of the hyperparameters of the covariance kernel function directly through data-dependent training of the Gaussian process without resorting to external tuning procedures. So, as we have learned before, we can now make simple predictions for a Gaussian process regression task by simple matrix computation operations. So very simple linear algebra. We can compute the predictive distributions at one or multiple arbitrary test locations after having observed a bunch of training data points for our Gaussian process. But for this to work out, we have so far assumed that the covariance function is fully specified, including all of its hyperparameters. And that's, a somewhat unrealistic assumption. In other machine learning models, we now have to resort to external tuning procedures to pick the hyperparameters of such, a model component in a data-dependent manner. A very nice property of Gaussian processes is that we can learn these numerical hyperparameters, which is sometimes also called the model selection problem of a Gaussian process, directly during Gaussian process training. And basically, Gaussian process training only solves exactly this problem, picking the numerical hyperparameters of a specified covariance function. What Gaussian process training does not help us with, and where we might still have to resort to external pruning procedures or at least other instruments, is picking the correct covariance function family. So let's assume we are operating under our now usual noisy Gaussian process scenario, where we have access to noisy training observations where we observe these y values here, which are a sum of the true function values f plus an error term epsilon. And now we know, and we also assume that this f here is a zero mean Gaussian process, which is specified by this covariance function. And I am now making explicit that the covariance function here depends on a vector theta of covariance function parameters or hyperparameters, however you want to call those. And as we have already seen in the lecture unit on the predictive distribution of a Gaussian process, we now know that this y vector here is jointly distributed by this multivariate Gaussian, which is zero mean, and where the covariance matrix here is made up of these two components. So this regular covariance matrix capital K plus a diagonal matrix with sigma squared, which comes from this variance component of the noisy epsilons, or of the noise epsilons. And because we now know how this y vector is distributed, we can now write down easily the marginal log likelihood of that vector. So I know this is a multivariate Gaussian, so I can simply write down its multivariate density here and then put a log in front of it to get the log likelihood. So let's quickly check that we recognize here the multivariate density of a Gaussian. I hope we can do that. So we have this normalizing 2 pi constant here. We also have here a matrix ky, and ky is simply an abbreviation for this guy here. And now we invert that and then also take the square root of that matrix. And here we have the, we compute the determinant of that matrix, and then invert it and take the square root. And here we have this regular exponential term of the Gaussian density, again using the inverse of ky. And because we are now considering the log likelihood, we can now nicely draw that log function here on the inside. This product here becomes a regular sum. And also for this third component here, this exp component, the log function and the x function nicely cancel out. So this first component I have now reordered a little bit and put here as the first component in the next line. Here you see this log determinant of ky component, and here you can see a normalizing constant, which is this guy here. And also you can see that these exponents here nicely go in front of the log now. And we can start now interpreting the roles that these three components play in the definition of this marginal log likelihood and its structure. And we should remember how the length scale parameters actually act on our Gaussian process model. So the more we increase the length scale parameters, the less flexible our modeled functions become, right? Because the larger the length scales become, the more smooth and the less wiggly and local and flexible our modeled and sampled functions become. Now, the first component, this guy here, which is this guy, that basically represents our data fit. And this data fit tends to decrease if we increase the length scale parameters. Obviously, because our model becomes less flexible in that case. And then the second component, which is this guy here, that can be considered as a complexity penalty, which only depends on the covariance function and not on the outcome values y, and that decreases with the length scale because the model gets less complex with growing length scale. And then we have this normalization constant here, which we basically can forget about if we simply want to optimize the log likelihood for the optimal parameter vector theta. Now, to visualize this, so we get a better understanding of this quite complex log likelihood function, I will now consider a zero mean Gaussian process with a squared exponential kernel and a simple scalar length scale parameter L, so I can visualize this nicely in a 1D plot. And I will now show how this data fit and the complexity penalty and also the overall value of the marginal likelihood develop if we increase or change the value of L. So on the right hand side here I visualized a typical simple toy example for Gaussian process regression with a univariate x and our normal real valued regression outcome y. And the left hand side shows now the data fit component of our marginal log likelihood, the complexity penalty, and also the overall marginal log likelihood. So this here is the red guy here, that's the data fit, that's this component, and you can see that this goes down if the length scale goes up, and here quite the opposite, the complexity penalty parameter goes up if we increase the length scale, so model becomes less and less complex, so we can like that more in the penalty, and the marginal log likelihood function here in blue is a combination of these two, so I can forget about the normalizing constant in terms of optimization. So this is basically just a combination of these two. And what we are now looking for when we optimize this marginal log likelihood is kind of the sweet spot of where data fit is good and complexity penalty is not so bad. And we can now check for a couple of extreme values. For example, we can check for a very, very small length scale or moderately small length scale where we have quite a lot of flexibility going on. in our modeled posterior mean function. And we might already tend to say that we are now beginning to overfit and we are beginning to model the noise in the observations. Yeah, actually it still looks quite okayish, but the smaller we make this length scale, the more we will start kind of interpolating these points or modeling the noise, the measurement noise in the observations. If on the other hand we pick a super large length scale, you can see that we now drastically underfit our data set because our function is constrained to be too smooth. And this here is the optimal point, the maximizer of the log likelihood with L equals 0.5, and that seems to balance complexity and fit quite well. And this is exactly what happens if we now optimize this marginal log likelihood. And in order for us to do that numerically, it's probably a good idea if we have analytical gradients available to us, so we can use gradient-based techniques, for example, like gradient descent. So one word of warning, this marginal log likelihood is usually not a unimodal or a convex function or concave function if we maximize it. So we have to watch out a little bit for this. So probably we need to either use like a gradient-based technique, a gradient ascent-based technique with restart, or we kind of have to combine gradient-based techniques with evolutionary techniques usually. What I want to show to you here is that you can derive an analytical formula for gradients of the log likelihood with respect to the kernel parameters theta j. And I won't read this out. You can do this with pen and paper using these identities here that I have also noted down as hints in the last line. And you can see that at the end you get your hands on an analytical formula for the gradient of the log likelihood P if, and that's an important point, if you can compute an analytical partial derivative of the kernel function with respect to its parameters. Yeah? So this depends now on the structure of your concrete kernel function you're using. For most of the popular kernel functions, this works and you can do this, but this needs to be assumed, or this needs to be given that you can do that. If you can do that, you can combine these two parts here and have your analytical gradient enclosed form available to you to make use of this in your gradient-based optimization technique. What's the complexity of all of that? How expensive is this? So the complexity and the runtime of training a Gaussian process is dominated mainly by the computational task of inverting our matrix K. So we have this matrix K inverse going on here, and this is an n times n matrix where n is the size of our data set. Usually we don't really invert that matrix, but we rather decompose it, we factorize it. Standard methods for doing that decomposition still require O of n cubed time, and that's quite a lot. So many machine learning models that only require squared O of n squared time in terms of the training data set size are still considered to be somewhat slow. For larger data sets, now we are here using up cubed time in terms of our training data set size. And this means that by using such a regular optimization scheme for the Gaussian process, it's pretty unlikely that we will be able to work with Gaussian processes on, certainly not super large training data sets, and even for medium or normally large training data sets, that can be a tough challenge, and the training might scale too badly for us to employ GPs in such situations. So usually it's GPs are much more interesting for smallish to medium-sized data sets, and we really want to make use of the nice spatial and stochastic properties of the model. If this K inverse here, or rather its decomposition, is known, the computation of the partial derivatives only requires O of n squared time per hyperparameter evaluation. So the computational overhead of computing the derivatives is small compared to this really bad component here of inverting or decomposing K. So using a gradient-based optimizer, if we can compute this decomposition here, seems to be somewhat advantageous. There's a couple of workarounds to still make GPs feasible for big or larger data. So we can, for example, use kernels that yield sparse kernel matrices, capital K, which are then cheaper to invert or to decompose. We can use popular subsampling tricks. So we can subsample the data through M points and then only do the model selection on these M points, which is also a super old trick for hyperparameter optimization. And in order to stabilize that, we might have to do Bayesian committee approaches where we estimate on different subsets of size M and then kind of integrate out over them. That makes it even, results in a runtime of O of n times n squared. Or, and that's a very popular approach, we can use low rank approximations of our kernel matrix K by using only a representative subset, so-called inducing points of M training data points. And there's, for example, this popular Nystrom approximation available. Or we can exploit the structure in K induced by the kernel. Sometimes exact solutions are available here, but that's usually pretty complicated maths. It's also not really applicable for all kernels, and really making GPs work for larger data sets is still a quite active area of research and is not to be considered a solved problem at the moment.